Okay, graphs of polynomials. So we now have explored the concepts of end behavior, right? That's what the far right side and far left side of the graph do. It's either both arms up, both arms down, one arm up, one arm down. And that end behavior was determined by the degree and the leading coefficient. We also talked about zeros, which real zeros are also X intercepts. And we talked about the different multiplicities. If you have a zero that happens twice, when you're solving and you get a zero that pops out 2 times, if it pops out an even number of times, remember it bounced off the axis. An odd number of times it goes right through. And we also talked about turning points, which were relative maxes and mins. Okay, so we are now ready to learn how to create a quick sketch of a polynomial function. We did one of these really fast at the end of last class, but today is going to be practice doing this over and over again. All right, so I want to graph x to the 4th minus 6x cubed plus 9x squared. First thing I'm going to do is try to determine the end behavior. What do the far ends of this graph do? All I need to look at for end behavior is the leading term. Is the degree of that leading term even or odd? Even. What is the degree? 4, yeah. The degree is the highest power on x. In this case it's a 4. So the degree is even, right? And the leading coefficient is 1, right? There's a little imaginary 1 there, okay? Degree is even, leading coefficient of 1. Show me with your arms what the end behavior is going to look like. Good, okay. So as x goes to positive or negative infinity, as you go to the right or to the left, both arms of the graph go up. Okay, so we know what the end behavior is going to look like. Now I'm going to try to find the x intercepts, which is zeros of the function, by setting the function equal to 0 and solving it. All right, so I've got my function equal to 0. For polynomials, pretty much the only tool we have is to just try to factor it, right? Just like cross your fingers and hope it factors, right? So this first one, is there anything that we can factor out of every term? X squared. So I've got 0 is equal to x squared times x squared minus 6x plus 9. Can you factor any further? Yeah, x squared minus 6x plus 9 factors even more. So I have 0 times is equal to x squared times x minus 3 squared. X squared minus 6x plus 9 factors to x minus 3, x minus 3. Then I set each factor equal to 0. Before I do that, I'm actually going to write out all 4 of my factors because I have some things that are being squared here. So I have 0 is equal to x times x. That's what x squared is. And x minus 3 squared is x minus 3 times x minus 3. So I've got 4 things being multiplied together, and I'm getting an answer of 0, which means one of those things, at least one of those things, has to be 0. So I set each factor equal to 0, and I'm running out of room. I'm going to jump up here. So x equals 0, or x equals 0, or x minus 3 equals 0, or x minus 3 equals 0. So I have 1, 2, x equals 3, or x equals 3. I actually have 4 zeros, but 2 of them were repeated, right? 2 of them were repeated. So my x-intercepts are going to be at 0 and at 3. What is the multiplicity of x equals 0? 2. That happens to be a 0 2 times when I'm solving. So that means that when the graph comes down to the x-axis at 0, it's going to bounce off because it's got multiplicity 2, an even multiplicity. And at x equals 3, that's also an even multiplicity because that happens twice. It's going to bounce off at 3 also. I'm also going to find the y-intercept. This is something we've known how to do for a long time. Just plug 0 into the function to get the y-intercept. And so I get 0 to the 4th minus 6 times 0 cubed plus 9 times 0 squared, and I get 0. All right, so I'm going to check for symmetry to see if this graph has any symmetry that can help me draw it. So if I plug in f of negative x, so let me rewrite the function here. F of x was x to the fourth minus 6x cubed plus 9x squared. If I plug in a negative x, if I get the exact same function out, right? If you plug in a negative x and you plug in an x and you get the exact same thing, then that's an even symmetry. If you plug in a negative x and you get the opposite function out, then that's odd symmetry. So we're going to plug in a negative x and see what happens. So for each x in this polynomial, I'm going to replace it with a negative x. So I've got negative x to the fourth minus 6 times negative x cubed plus 9 times negative x. And then I simplify this. Negative x quantity to the fourth, what does that simplify to? It's x to the fourth. Oh yeah, for the last one, there's a squared on there. Thank you. Yeah, so if I take a negative x and I raise it to the fourth, that means negative x times negative x times negative x times negative x. 4 negatives make a positive. X to the fourth. Negative x cubed means negative x times negative x times negative x, which is negative x cubed. So I've got negative 6 times negative x cubed, that becomes plus 6x cubed. And then the negative x squared becomes positive x squared. So I have plus 9x squared. All right, this guy, is that exactly my original function that I started with? Is it exactly the opposite of the function that I started with? No. So this graph has neither kind of symmetry, neither even nor odd, right? Because this thing I came out with, it does not equal my original function f, and it does not equal the exact opposite of the original function either. You're either looking for the original function or the exact opposite, where every sign has changed. It's not equal to either of those, so I have neither kind of symmetry. Okay, so now I'm going to try to sketch what I've got here. Just take all this information I've gathered and I'm going to try to sketch it. I know my end behavior is both arms up, so I've got, at the far ends of the graph, my arms are going up. And I have an x-intercept at 0 and at 3, both of which are bounce-off kind of x-intercepts. So I've got a 0, one at 0, and one at 3. And my y-intercept is also at 0. So this point is an x and a y-intercept. So now I'm just going to do a rough sketch where I try to connect all the pieces that I know about. So this is my end behavior, and it never goes through the x-axis, so this has to go up to the graph like that. And this has to bounce off here and bounce off here, so it's got to look something like that, and then go and connect with the rest of my graph. Now the height of this little relative maximum here, you can't tell how high that is, right? This is just a rough sketch of the general shape of my graph. How many turning points have I drawn here? Local maxes and mins. 3. Remember there was that theorem yesterday that said when you had degree n, you can have at most n minus 1 turning points. The degree of this function was 4. So does it make sense to have 3 turning points? Yeah, that's allowed. That's the most I can have, so that's allowed. So I haven't, it's just a quick check to see if you've done something wrong. That make sense? What we're doing? Okay, you try one. Try to graph this cubic. Okay, let's look at number 3 together. Some of you have moved on, that's fine. Step 1, end behavior. So we have an odd degree and a positive leading coefficient. So what are the arms going to be? Right? One arm up, one arm down, and it's right arm up. Right? So the fact that it's an odd degree tells you it's one arm up, one arm down. And the positive leading coefficient tells you that it's the right arm up. So I've got the end behavior. I drew it right in the graph. Okay. X intercepts I find by factoring and setting it equal to 0. So I could factor out an x here, and I'd have x squared minus x minus 6. And then that factors further to x minus 3, x plus 2, which means I have 3 zeros. X equals 0, x equals 3, and x equals -2. What are the multiplicities of those 3 zeros? They're all 1, right? They all have multiplicity 1 because they came from a factor that only showed up once. Okay, so they all have multiplicity 1. Which means that they are zeros where the graph goes right through the axis, because 1 is odd. So I've got 0, 3, and -2. And my y-intercept, f of 0, when I plug in here, I get 0. So I already have the y-intercept graphed there. Did this guy have any symmetry? No. If we plug in a -x, we get -x cubed minus -x squared minus 6 times -x. And that becomes -x cubed minus x squared plus 6x. That is not exactly the same as my original function, right? It's not exactly the same as this guy. So it means I do not have y-axis symmetry. And this was a little bit confusing, I know. Y-axis symmetry is the same thing as even symmetry. Origin symmetry is the same thing as odd symmetry. So this is not exactly the same, so I don't have y-axis symmetry. Have I changed every single sign? I changed the x cubed, I changed the sign on the 6x, but the sign on the x squared is the same, right? So every single sign from my original function did not change, so this is neither, right? If every single sign changes, then you have origin symmetry. Okay, so now I can try to sketch this. What's the maximum number of turning points you can have for a cubic polynomial? 2. Okay, so I got to try to draw this thing, connecting my end behavior to my zeros. I got to have the right behavior at the zeros going through each one, and I can only have 2 turning points. So something like that. This kind of looks bad over there. There we go. Does that make sense? Okay, so we'll do another one. Same exact 5-step strategy, except I've done some of the hard work for you already, in that I already factored the function. I already have it written in completely factored form. So you can jump right to finding the x-intercepts, and you go, oh, this is awesome because it's already factored. I'm just going to set each factor equal to 0. What's the catch? We'll see. I skipped the end behavior for a reason. So when I solve each of these, I get x equals -2 and x equals 2. And this guy, I get x equals 0, but what do you know about the multiplicity of that one? It's 2, yeah, which is even, because x was a factor twice. So this one is multiplicity 2. Both of these are multiplicity 1. So I can put those in. I've got a 0 at 0, at -2, and at 2. All right, now let's think about the end behavior. So the end behavior is the highest power of x, right? It's the highest power of x when everything's all multiplied out, but I have it factored. How could I figure out what the highest power of x is in this polynomial? Yeah, just multiply it all out. I could actually do all the work and multiply it out, or I could just add up all the exponents, because I know that when I multiply like bases, you add the exponents. So I've got a 2 here, I've got a 1 here, and a 1 here. So I'm going to say my degree is 4. What would my leading coefficient be if I multiply that all out? -1. Yeah. So you can try to like sort of pretend like you're gonna multiply it all out and just figure out the degree and the leading coefficient. Or you can do the multiplication if that helps. So let's do this. For this one time, we'll multiply it out. We've got negative x squared times x plus 2, x minus 2. So I'm going to start by multiplying these two together, because that's easy. I just do it with FOIL, and I get x squared minus 4. And then I still have to multiply by that negative x squared. So I'm going to distribute that. So I get negative x to the 4th plus 4x squared. And now that it's all multiplied together, now you can read off the degree and the leading coefficient. Which means the end behavior is going to look like, show me with your arms. Very good. Negative touchdown. All right. So a little bit more work to figure out end behavior, but it's a lot less work to get zeros if I give it to you in factored form. So put in my end behavior. And then at the -2 and the 2, it's supposed to go through the axis, and at the 0, it bounces off. So something like that. And, oh, I didn't do the y-intercept, but it was 0 anyway. Plug in 0, you get 0. Okay, let's see if this thing has any symmetry. It looks like it might from the sketch that we've already drawn, but let's just check to make sure that we are right. So I'm going to use the multiplied out version of this thing, which was negative x to the 4th plus 4x squared. And if I plug in a negative x, I get negative x to the 4th plus 4 times negative x squared. Negative x to the 4th becomes positive x to the 4th, because you have negative times negative times negative times negative, but then we still have this negative out front. So this is negative x to the 4th plus, and then negative x squared is x squared. Forgot my 4. And that is exactly my original function. So in this one, I have y-axis symmetry, which we thought might be the case from the graph. In a 4th degree polynomial like this, what's the maximum number of turning points? 3. And I have 3, so I'm within the rules. So I think I've drawn this correctly.